to help us do it. But what we're going to start off with is to talk a bit more about refactoring, because I've had a few people ask questions about that, so I thought I'd go through that with the group. So let's sort of talk about what we were sort of saying at the end of one of the lectures about refactoring at different levels and using the different levels of testing to help us. So in week 3 I said refactoring changes structure, not behaviour. I probably said that in weeks 2 and week 1 as well, and possibly in week 4, but I definitely said it in week 3. And so just to sort of really hit this home, what do we mean by behaviour? Well, we mean the function that's performed by the code or the interface that the code presents to the world, and that interface may take probably take the form of an API, an application programming interface, which is what's generally documented for developers to use, and that could be in the actual language of the that could be in the language that you're coding in, or it could be a sort of a remote API, such as like a REST API or a web API of some description. Generally the interface is, I suppose, more obvious in object-oriented programming, because it's the things like the methods within the classes and that sort of thing, and the parameters they take. But obviously all code has an interface at some level. So the reason why we say that a refactor doesn't change behaviour, and the fact that includes the interface, is that if you change the interface, then you're probably changing what the code can do or how it does it. So it is definitely a behavioural change, and so we generally not call that. We generally not call that sort of thing a refactor. Certainly not at the unit level. And if you remember again from week 3, we talked about the fact that we could actually change some of these behaviours, so long as we only did it in a very targeted manner. We talked about how each level of tests provides protection for the levels below. So, for example, if we do need to change the way some of our code works at the unit level, and we do need to sort of change the interface there because we can see a new function on the horizon, then we can call it a refactor within the integration tests, in the sense that we make sure that the integration tests all still pass, and so on. And if you remember as well, we said that if the acceptance tests are changing, then that's clearly new functionality or changed functionality, probably all the way through the system. So you can't refactor at that level, but you can refactor to all the others. Does that make sense? Are there any questions about that? In terms of, so you're shaking your head. Are you shaking your head because it doesn't make sense, or shaking your head because you don't have any questions?
I'm shaking my head because I'm tired, so I'm not head up with one. So. Okay, no worries. Right. Okay. So let's go through some of the frequently asked questions that I tend to get from people about refactoring. We have some of these this year, but we've had them in previous years as well. So worth going through, I think. Okay, so what if I split a complex method up into smaller private methods? So, can anyone think about? Can anyone tell me whether that's a refactor and which level it's a refactor at? I don't have any thoughts about that. So, a complex method into smaller private methods. Yes.
It's a refactor and it's at the unit level.
Yes, it's a refactor and it's at the unit level, and the reason for that is that we're not going to change any interfaces. So we're not going to change any interfaces because all we've done is we've created some private methods, and so we can't test private methods because they're not in the. Well, I mean, okay, you can sometimes test private methods, but it involves doing fairly low-level things in languages. So you tend not to test private methods, but the interface hasn't changed, and the function which is then going to call the private methods will just call them, and hopefully
that's going to not break any of our tests. And if it does, then we've done something wrong. So the thing is the private methods are not part of the public API. So they've not changed the interface.
So what if the interface have changed, but in terms of appearance, not in terms of input and output?
So if you've changed the interface at the level of the public API, then it would not be a refactor at the unit level.
Even if the input and the output are the same?
Well, how would that change the interface then?
I mean, just change position of things, the look and feel, the idea.
So when you say change position, do you mean...
User interface.
Well, if you change the user interface, then you've probably not changed anything at the unit level, or maybe even the integration level, but you will have changed something maybe at the system level, or maybe at the acceptance level. So if for example, the customer says, I want to make sure people can choose where they're flying to before they choose the dates, and they swap those around, that would probably be a change of an acceptance test. So that would be it would be changing something, right? So it would be changing, if you're doing tests of the user interface, then you might need to change those tests if you've changed
So it's
those
not a
things.
refactor.
So it's not a refactor at that level, no. Yeah. But you'd hope that all the unit tests still passed, because it should still be calling the same things underneath. So the unit test should not depend, right, on where things are in the user interface. So I'm also possibly conflating the use of the word interface here. So I'm generally talking here the interface to the code, as in the parameters, the method signature. But it's a good question. Okay, so if we were going to do this then, if we were going to split this complex method into smaller private methods, what would be the first thing we do? Before we do a refactor, what's the first thing we do? Anyone? Run the tests. Yes, so if we're going to refactor, we want to be sure that the code works before we refactor. So the first thing we do is to run the test. So I've got myself into the stage, so I don't do so much programming anymore, but when I did it all the time, I got myself into the sort of mindset that I just sort of ran the tests, sort of almost like muscle memory. It's almost like the other thing I do for muscle memory is just running git status all the time to remember where I am. So I spent, I just find myself running the tests, just sort of, even if I didn't need to. I just find my fingers just running the test all the time. So yes, you run the test first, then you do the refactor, and then what do you do?
Interesting.
Sorry?
Test again.
Test again. Make sure, and then you should run everything probably, just to make sure you've not added any regressions. So at this stage, we expect that all the tests are going to work. They might intermittently, all pass. They should all pass. At this stage, they might intermittently pass and fail as we are refactoring, and they should obviously definitely all pass at the end there. Okay, so any questions about that one?
When you say run the tests all again, do you mean all tests in the entire application?
So you might do. So it depends how big your application is, right? If you've got a huge application and you want to test across various operating systems and with different dependencies loaded, then you'd still probably leave that to the continuous integration. But you might run. So here you might, if it's a really big code and you can actually, if you've got your tests split up in such a way that you can run tests for different modules separately, you might just run the tests here for the module you're going to refactor, and here you'll probably run all the unit tests, which should hopefully not take too long. But if they did, you would just push it off to the CI. Yeah. Okay. So next question is, what if I'm removing a public method and I no longer need the test that yeah, so there'll probably be a test for a public method. What if we're removing public method and no longer need the test? So, is this a refactor, and if so, at which level? Anyone? Hazard a guess? So we're removing a public method, so we're going to change an interface somewhere, we're going to change the API.
This public method functionality, is it transferred to a different method?
We're just, at this stage, this was just saying we're just removing it. Yep.
This is an integration.
Yes, so this is a test. So if I remove a public method without doing anything else to the tests, the unit test should fail, because there's now no longer a method for one of the tests to check. So it's definitely not a refactor at the unit level. But if we don't need this method elsewhere, if we've decided that the functionality is such that this public method is not being used anywhere, then it should be a refactor at the integration level. So everything else should work. Of course, if you remove the public method and literally everything else fails, all levels, then that's probably resulted from the fact that you're doing this as part of some larger changes, or adding functionality or removing functionality at a sort of system level. So where this might happen is because in TDD we say things like, we said the red green refactor, do the minimum to get things to pass and then go back and clean up. Well, it might be that at some stage you've added a feature and you've managed to consolidate where the functionality of that public method goes after adding something else. So this might be a refactor just to clean up some code which isn't being used anymore. If you remember, I think it was back in the first week when we were talking about just testing, before we started talking about TDD, I mentioned that having code that might actually pass all the tests but isn't being used is seen as a code an issue, because having code hanging around it can leave you if it's not being used, it can leave you sort of in difficulties if it's not being used and you then come to rely on it, but people don't think you are. Okay. So it's a refactor at the integration level. We are changing the unit test. So what do we do first if we're going to do this change? Run the tests. This is going to get repetitive, sorry. I'm kind of obsessed with testing. So you run the test to ensure that they pass. Then I suppose if we're following sort of TDD, so this is interesting actually. So how do you follow TDD if actually what you're doing for moving stuff? I mean, we've sort of said things like you should write code if you've got a failing test, and if you haven't got a failing test, you shouldn't write code. I think this is one of the situations where you probably can't actually use TDD in any sensible method, because if you think about it, if you were to remove the method and then run the tests, you'd have a failing test, and TDD dogma would say, well, you've got some work to do. So what I would suggest is you just remove the test and then remove the method, maybe at the same time, anyway. And then what would you do then? What would you do after doing that? Go on. Run the tests. Yes. If you learn nothing else from this course, it'll be, to keep running the tests. Okay. Any questions about that one? Good. Okay. Right. So here's a question that I think you asked just before. What if I'm moving a public method between two classes? Is this a refactor, and if so, at which level? Any offers? So
Both unit and integration level.
So it's definitely not a unit test. What level did you think it might be?
Integration.
So it's probably not at the integration level either, because you're actually changing the interface of at least 2 classes. So you might think of something like unit tests are checking the functionality of individual functions or methods, and integration tests are checking that groups of those things work together, possibly within a class. Then possibly outside a class as well, but generally think about it within a class. Then at the system level, you're definitely making sure that modules or classes work together. So if we're changing the public interface of at least 2 classes, I mean I've said a class here, but if we're moving a public method between 2 classes, then we are obviously changing the interface of at least 2 classes, then it's going to be a system level integration. So we might expect, well, we're in the middle of doing this, we might expect the unit test to fail, we might expect the integration test to fail, but the system tests should pass because we're just moving functionality. The functionality is still in the system. Okay, so if we're doing this, what do we do first? Run the tests. Then what will we do? Think about it in a TDD way. Anyone? So we're going to do something to the tests now.
Change the test.
Yes, so we change the tests so that it's going to test the code in its new location. And at this point, all we've done is change the tests, and we should get a fail somewhere, which in TDD world tells us we've got some work to do. And that work is hopefully easy. I mean, it might be a copy and paste, it might be a bit more complicated, but we can move the code to the new class. And then what do we do? Run the tests. Yes, good. So obviously, there are tools that will just do this for you, right? Take it people who generally have used tools like Eclipse before. So Eclipse has the magic refactor button, which you select something and you can hit refactor, and it will say, "What do you want to do?" And you can split it into methods, different methods, or you can move it to a different class, and it will do all this work for you. May not change the tests though, so that's always something to think about. You might need to change the test yourself before you let the IDE do the work. But it's always worth running the test beforehand, running the tests afterwards, even if you're using some fancy tool to do much of the work for you, just to make sure that it is actually doing what you expect it to do.
Based on the last 2 slides, I came to the conclusion that whenever we have a work at one level, then the refactor will be up
yes,
one level.
Exactly. Yes, that's the thing. So if we go back to the animated slides, if we go back to the target, that's exactly what this is exactly what I'm representing here. So if you're refactoring in the unit part, right at the code, then you'd expect the unit tests to not have to change because you're refactoring at the unit level, and if they did change, then it's no longer a refactor. You're implementing new functionality or something like that. It's not a refactor at the unit level. If you do need to change the unit tests, then the integration tests should at least still pass. So they're giving you. So think of these as shells of protection, and so each time you should be able to ensure that you've not broken things further out while you're doing it. Okay? Okay. So, how do we know when to refactor? Well, there's a number of different things. Can anyone got any thoughts on this? We've not really talked about this, so any thoughts about why you might refactor or what to look for? Yep.
If I want to improve the internal qualities.
If you want to improve the
internal quality.
Yes, exactly. So this is a lot of refactors, especially when doing TDD, because the mantra and the pushing the point to the point of breaking point is that you always do the minimum while you're in the TDD loop, and then you go back and improve, and some of that is to improve the internal quality, and that might be to do something like check for complexity. So if things are overly complex, then they are difficult to be sure that they're working, or difficult to understand. So the test will tell you they're working, but if it's super complex, you might struggle to refactor it even with the test to tell you you've not broken it. So there's a couple of metrics that one could use. There's more than these, but there are these are some of the quite common ones. There's the ABC metric, which goes through your code and for each method will count the number of assignments you make, the number of branches you've got, the number of calls you make, and it assigns a score to each of those things, and then it'll give your method a score. And then you can sort of say, you can actually have tools and you can say, well, I think anything with a score above 10 we probably need to think refactor, and the tool will just go through and it'll just analyse your code. It's a static analysis, and it'll tell you that a method's too complex, and that might be something that you go in and refactor. Cyclometric complexity is a quantitative measure of the number of linearly independent paths through a program's source code. So this is, I remember a couple of weeks back I was showing you how you only need a couple of branches with true and false, and you end up with many paths through the system. So cyclometric complexity sort of is a number attached to that. So if you've got lots of different, lots of branching in a method, it might come out as being complex in that way. So that's another good thing to check for, and you would consider refactoring high-scoring methods of those. Now, of course, you can generally, some things just have to be complex, right? So one has to. So sometimes it's difficult to make everything super simple. Sometimes things are just complex, and so these are all tunable. So you can decide within your project, what are we going to call a complex method, and what are we going to set these things as. So another thing you might look out for is structural similarity. So things that are doing exactly the same thing. This is, of course, something that you might have with TDD, because you're working at the unit level when you're doing TDD, and you're just concentrating on getting the particular test to pass. So you're not thinking at that time about should I reuse that code? But then you go and refactor and you can reuse code. So looking for structural similarity. And the interesting thing is, of course, is that sometimes code you've written in two different places, you've maybe not looked if it's in different parts of the file, you may not have actually noticed that they're the same, or they may not even look particularly the same, but when you've got a static analyzer looking at it, it might actually show you some structural similarities that you couldn't see. So there'll be a set of tools which can check for that sort of thing as well, and that would be something you would do. And really the important point here is don't try and do this by eye or by hand. It's take a long time, you might get it wrong, so use the tools. The tools are out there. Most languages will have these sorts of tools available, and indeed there are online services to help you do this sort of thing. So this is one I quite like, Code Climate. It works for pretty much any language that you might ever want to use, and it will actually use those sorts of metrics I've just described, and it will give your code a grade point average, which is a bit of an Americanism, but that we can work with that. So what it does is it assigns a grade to each class, A to D or fail, and then you get a final score. So I think it's something like you get a 4 for an A, and a 1 for a D, and a 0 for an F, and then you get this score here. So this code looks like it's not too bad, but there are a couple of bits which are obviously fairly low.
Does it mean that this program has 4 classes?
No. This would suggest that there's probably. I mean, it looks like there's one red class getting a D and one class getting a C. So it looks like there's 3 classes getting a B and then I don't know, a load getting A. So it's proportional. So most of the classes are getting an A. It looks like there. Okay. So this sort of thing's really useful. It's free if you're using an open source. If you're writing open source, you just connect it into GitHub, and every time you push, this will just go away and regrade your code. So that's quite nice. And one of the things that's really nice that these sorts of tools can do is they can help you manage this balancing act between churn and quality. So keeping things like really keeping things the quality high and being very mindful of that is obviously good. But sometimes, as I say, things just have to be complex, and things it's possibly sometimes you might take a strategic view that keeping something high quality would take so long that maybe it's not worth it, and this sort of graph can help you decide where you're going to go. So churn is how often something changes. So in this case, churn is saying that the further along you are down this axis, the nearer you are to that side, the more times the code has changed in commits. So this code here hasn't changed at all after it's been written. That's good. And this code's changed a bit more. This is a bit more. That one at the top, loads. It's changed really a lot. So on this graph, we're saying that down and left are better. So this is where we, an ideal about where we might be. So we might, and the reason why this is very helpful is that if we had some code which was of poor quality, so high up, but it was here, then we might not decide to actually spend too much time refactoring it because it's not changing. So it might be poor quality, but it's constant, and we can say, well, why would we necessarily, if we've got finite time, right, and we've got deadlines to meet, we might say, well, let's not refactor that at this stage because we're not seeing it change a lot, so we're not having to look at it. So it might be poor quality, it might be difficult to read, it might be complex, but because we're not having to change it, does it matter? Maybe not. And so up in that far right-hand corner, that is a candidate for refactoring because A, it's poor quality by those metrics, and B, we're changing it all the time. So every time someone looks at that code of poor quality, they're probably having to do a lot more mental effort to decode it into their own mind. It's complex. It might be a very, very large class. All these things, and so every time someone who looks at it, they're going to have to spend a lot of mental effort to change it, and it's changing a lot as well. So we might say that anything below the curve, we might not need to worry too much. We might say, okay, so this has got like a C grade, but it doesn't change too much. So let's just leave it for now. Now, if we start to see this creep over here and get worse, then refactor and bring it back. But we can think a bit. We can think quite carefully about how much we're going to do. And churn on its own is okay. You've got to change the code sometimes. You've got to add new things. But if we're changing it a lot, let's just try and keep the quality as good as we can, so it stays below the line. Okay, so I'm going to come back to this in a minute with a confession of sorts about some of my own code. So that's some code I wrote a few years ago now, but I'll talk about that in a minute. Okay, so another thing we get asked quite a lot is how much testing is enough, so I think it's worth talking about that as well. So with test-driven development, you have these tests to prove that the code works for normal usage and for scenarios that you have thought about, and that's key here. So you're writing in TDD, you write a test, you make sure the code then passes that test, and then you refactor a bit, and then you write the next test. So you have tests for everything you've thought about, and generally you will think about lots of different things, and that'll be fine. But there are certain things that are quite difficult to test, and you might have external factors that you can't control, and actually might be quite difficult to test using TDD. So this might be things like if you're relying on a remote server and it's down, what do you do? Or you're writing an Office application and you want to handle a disk full error carefully. So I've used programs before, probably old versions of Office or something like that, which just didn't tell you if the disk was full. So obviously, disks being full is quite an odd occurrence these days. It probably doesn't happen quite so much. Lots of what we do is in the cloud, and disk space is infinite in the cloud, so that's fine. But there were times when you'd save a Word document to a floppy disk, and if the disk was full, Word would just go, "Yeah, I've done that." But if the disk was full and it couldn't do it, it might just have left you a zero-length file, and that might really annoy you. So testing that sort of thing is important. And what happens if you just yank the power cord out or something like that? So how does your system cope with all these different things? If there's unexpected power failure, is your database going to be in some horrible state or something like that? These things are really difficult to test, and they're probably not something you want to even attempt to test in TDD. So how much testing is enough? Well, you probably should test that at least. You should probably test that. I mean, I don't know how one would test that. But there you go. Okay. So comprehensive tests. These are some questions we get as well. If all your tests pass and then you change something, what should happen? Anyone? So all your tests pass and then you change something and then you run the test again. So let's give an example. Let's go into the code and randomly change somewhere that says true in the code into false. What should happen if you run the tests?
Might fail or pass.
Should at least something should now fail. A test should fail. If you go into your code, change a true into a false, or a 0 to a 1, or a string to a float, then if you rerun your tests, something should fail. And believe me, you'd be surprised how many times a test doesn't fail. So if nothing fails at that point, then you're missing a test. Okay? So if you can go into your code and randomly make changes, and then the test still passed, then you don't have as comprehensive test coverage as maybe you thought you did. So, interestingly, what you could do is you could go through your entire code base and take every possible chance to change something individually, and then rerun the tests. So even for like Hello World, that would take some thinking about. So you should never try and do this by hand. But there are tools that will do this automatically. So there are tools that will exercise your testing regime by going through every assignment in your code, every branch and every call, and it'll just change it to something syntactically correct, so it doesn't just break the code in terms of it just failing because it doesn't compile or doesn't run. But it'll change it to something sensible but different, and it'll rerun the test. And this can take, even on a modest code base, you have to run this overnight and let it go through. But you'll get a list at the end of all the tests you're missing, and it'll be horrible. I've run this on some of my code once, and I've never run it again because it's just horrible. But there are tools to do this. And if you're in a, we talked, didn't we, a couple of weeks ago about using. I think it was last week actually, about using TDD and Agile within formal processes. One of the formal processes that you might do is run tools like this to just absolutely constantly, batter your code with tests.
So these tools will come up all with all cases missing in the test, or will change my code?
It will come up with all the missing cases.
Yeah.
Yeah, it won't actually then add the cases for you, unfortunately. I mean, maybe some of them could be done like that, but where the code requires some semantic knowledge rather than just syntactic knowledge, it would probably struggle. Okay, so we're sort of saying at this point that we should test all our code, and code coverage is a measure of how much code the tests actually exercise. So I think in the first week of the course, one of the introductory exercises is to run the coverage test, isn't it? So you've seen an example of this. So there's online services which will do this for you. So coveralls is one that I quite like, and again it all just connects into your GitHub environment. So what happens with coveralls is that if you're running your continuous integration directly off of GitHub, you can then have it put the results of the tests straight into coveralls, so it will manage that for you and tell you what's going on. So as an example though, why coverage is not the panacea that necessarily you might think about is that this file here has 71.5% test coverage. That sounds pretty good to me. That's not bad. We might say that's enough. But so it's not a very long file. This is an example in Ruby, by the way, rather than Python. So when I originally wrote this course, I was doing a lot of programming in Ruby and didn't have any Python examples to hand. No matter. The point is obvious, I think. It's got 71.5% test coverage, which sounds pretty high, but most of this code is just, defining classes and modules, or pulling in external code, or defining the method. So the actual code which is doing anything, so this is reading a file out of a zip file. The actual code which is doing anything hasn't been covered. It's in red. It hasn't been tested. So the problem with test coverage is that it shows that this code has been read because it has to read these bits of the code to build the structure of the code in memory. But this method was never called by any test. So these lines, opening the zip file and reading from it, are never called. So that's kind of useless. Looks on the surface like it's got good coverage, but you need to look at it and check the actual code doing anything is actually being exercised. So that's a good example of being wary of the raw numbers.
Can we call the grey area source code fixtures?
Can we call these source code fixtures?
Yeah.
I don't think so. I've never heard them sort of described by that. I think these are just the sort of the structure of the code. So I mean, it's all read in and it's been parsed, and so I've not made a mistake with missing a bracket there or anything like that. It's fine. But this method's never called, so that code's never exercised. And it's surprising how often that sort of thing can happen as well. So worth keeping track of this sort of thing. And so we can have a look at the whole project. So project test coverage 85%. I mean, that's pretty good. If you just so 100% test coverage is not necessarily required, and there's lots of arguments on the internet. I mean, okay, that's a tautology. Lots of arguments on the internet, but there's lots of arguments on the internet about how much you should be aiming for code coverage. And generally, I think the consensus is that anything over 90% is pretty amazing. Anything over 80% is probably pretty good. And you wouldn't necessarily, certainly if you're on a stretched timeline, you probably wouldn't necessarily want to spend too much time worrying about code which is 85% covered. But then that's at the project level. If you look at the individual files, there's this one at the top here which has only got 36% covered, so that's barely tested at all. And if you remember, if you think back to this example where we've got a file with 71% covered and all it's done is just read it in, that's probably what's happening there. It's just a bit more of a bigger file. So so yeah, so there's some pretty bad files there, and so the project as a whole is really well covered, but no, we've got some really big gaps. So we've got 25 files in this project, all but 9 are at 100%. Only 3 files are underneath 90% coverage, but one of them's at 36, and that could be a big danger, especially if it's high churn. So why do we do all this? Why are we doing all this? We keep talking about whole team responsibility and everyone looking after the code, and this is all about maintaining quality. Another one of my obsessions is that if the code is of high quality, then anyone should be able to look at it, understand it quickly, work on it, keep the momentum of the team going. So we want to maintain quality, and this is important for the shared ownership of the code, where we're all working on the same thing, we're all looking after the same code. So we must keep the quality consistently high, so there are no surprises in there for anyone, hopefully. We want to keep this minimal effort required to add to change or maintain what is there. And if we've got bad quality code, every time we look at it, that's technical debt. That's us having to spend maybe a day adding a change rather than half a day or something like that. If we've got to keep very complex code sort of stacked up in our head. So I said I'd do a brief confession, but we're at 10 to 11 now, so it's time for a break. I'll do the confession after the break, so if we come back here at 11 o'clock and we'll pick this up where we left off. Okay, so I rather left us on this cliffhanger. I said I was going to confess something a bit. So we just talked about why it's important to keep quality high and some of the tools we've got available for us to at least help us monitor the quality, if not actually do some of the work to do that. That might be down to us. So this graph I alluded to before is a graph of some code that I wrote a while back. So it's so this one up here, let's look at that. It's complex, it changes a lot, and just to sort of make it worse, it's got really bad test coverage. So it gets an F, a fail in code climate, and it's only got 62% coverage. So that means that I'm changing it a lot, which means that every time I run the tests against it, I'm not actually getting a full picture as to what I might have broken or what I might not have broken. So it's obviously ripe for there's problems, and even worse than that. At the time when it was like that, I needed to refactor it. So I needed to completely change the internals of that class because it was very messy. There's lots of technical debt, but I didn't have the and it's very complex. But I didn't have the tests available to be able to do it. So what do I do? Where do I start? You think? I need to refactor it. I want to be able to rely on tests to make sure I'm not breaking functionality, but I don't have enough tests. So what should I do?
Increase your tests.
Sorry?
Increase your tests.
Yes. Basically, I need to start writing more tests for this class. Get the coverage up to something more reasonable, given the amount of churn. The amount of churn it's got, I probably want to get the coverage up to about 90%. So there's a reason why there weren't many tests for this, by the way, which was actually it was very difficult code to test. The code was some worker code that was called by some other code in a different process. So there was a web app, and sometimes when users did certain things, something else would go away and work in the background to do something, so that the web interface for the user was slick and it didn't hang while it was doing this sort of thing. And this was some worker code to do that. And that just means that it's very difficult. In this case, it's very difficult to test because it's running completely outside. It's part of the application, but it's running outside the bulk of the application, so it was difficult to test. So, and it relied on lots of external services and network connections and things like that. So basically, there weren't tests. It was lacking tests for some, good reasons or some reasonable reasons. Okay, so how does one test things that has lots of dependencies on external things and so on? Well, we talked. Was it last week? I mentioned things like I mentioned stubs. So let's talk about those. And there's also this other thing called mocks. So a stub, which is a simpler thing, is a method which is used as a stand-in for something else. So these are really useful. It can simulate complex or long-running functionality. So it could have been something, use this sort of thing, and it can replace functionality on a remote machine. So basically, a stub gives us something that we can call from code that we are testing, so that it doesn't rely on external things or network connections or things like that. So an example of a stub might be, say we're testing a method which calls out to a database, and we don't, for the unit test, we don't want to have the database running. That would be something we'd do in the system test, probably, not the unit test. So we might actually, instead of calling the database, we might replace the database with a stub, which just returned a value that we can expect, and just test that connection is sensible, and what we do with the data when we get it back is okay and is working. So it can replace functionality on a remote machine, can replace interface code for an external device, or it can be a substitute for code that we haven't written yet. So sometimes you get sort of deep into writing an application and you need to test something, but how can you test part A if it relies on part B and you haven't written part B yet, or one of the other team are writing part B in the same sprint, so it's not ready yet. So at that point, you'd have some idea about what the interface of this missing code might be. You'd have had that discussion in the sprint planning, and so while you're writing something which is relying on someone else's code, you could implement a very simple stand-in. So, for example, let's look at example stub. So we use this example last week about reading a sensor. So we've got some code which is going to poll an external thermometer somewhere, and if the temperature is below 0 or equal to or below 0, it's going to print freezing. So it's not very exciting, but that's what it's going to do. So when we're testing the fact, so what we need to do is we need to test that if this temperature actually is 0 or below, we want to actually test that this is printed. And in these unit tests, what we don't want to have is a thermometer connect to the computer, because if we have that, then where's that thermometer going to be? It's going to be, we have to have a freezer next to the computer where the thermometer is going to be in it. And then what happens if we want to do something else where we want to check, whether the temperature is over 30, and we can say, be careful, drink lots of water. Then we'd have to take the thermometer out and wait till it, heat it up to 30 so we can test that one. So we don't want to test at that level with actual devices. So we'd have a stubbed method on this outside class, which just returns 0 for this test. And that'd be all we need to do, because we're not testing this method here. We're testing that freezing is printed if that if statement is fired. So we can use a stub method. So this is really useful. Now, obviously, this is all we need to do if we're only checking for 0. But if we wanted something to give us a bit more data, or say return 0 first time, return 30 second time, return 100, that sort of thing, we might want to have something a bit more complex. But this means we can test this. We can test this a number of different ways. We can check these things work. So we want something slightly more complicated, and that's where mock comes in. So mock is often described as a super stub, and the reason mocks are useful. Has anyone come across mocks, by the way? Yeah. So a couple of people have seen these. So the reason mocks are useful is they have knowledge of context, and so they keep. They have some knowledge of the environment which they're in, which you can provide to them, and they keep a track of what happens to them. So they're a very useful thing to then run various tests against once you've done something. So they can return different results in different contexts, and they are actually an active part of the testing process. So they can have their own assertions. So a mock, you can set up a mock to actually assert that data is actually passed to it. You can assert that things like maybe methods within it are called in a certain order, and you can check that other interactions have happened. So this is all it's all quite useful to check that things are happening deep in your code that you might not be able to test in other ways. An example of this might be, we talked earlier about it's difficult to test private methods because they're not part of the public interface. So one thing a mock could do is, if you set up a mock to mock up against an object that you're testing, that could actually keep a note of which private methods within it are called. And so you could check that a public method at least calls the private method with the thing you would expect it to call it with. And so if that test passes and the private method is called with the thing you expect it to have been called with, then you at least have some confidence that the method is doing exactly what you expect, and that the private method is being called as well. So I'll give you an example of a mock, and unfortunately I haven't got a very good. I've never been able to find a decent example of a concise example of a mock in Python. So I'm going to give you one in Ruby because it's a bit more readable. And
how about the one in our project, mock database?
So yes, so that's the mock database in the project is called the mock database. But really, I would say that one it's more of a series of stubs. So it's not actually a mock in the sense of it's got all this other knowledge about itself inside. So it's almost a stubbed class. So you've got an entire class full of stub methods. So I might have called that I didn't write that. I didn't write that class, and I might have called it stub database if I'd written it myself. Okay, so I'll give you an example in Ruby, and the reason, so it's not in Python, so sorry about that, but it does read quite nicely, I think, and should show what we want a mock to do. Mocks, so Ruby's a much lower ceremony language than Python, so methods don't have to have brackets on them if you're not giving them any parameters. So you can actually you can almost write sentences in it if you're quite careful. So what we're going to do here is this is the call to actually mock something, and we're going to mock this class, which is the server class in the T2 server module. So we're going to mock the server, and then so just the calling of that creates a mock of this class and returns it. So then everything we call after that is called on the mock, and every time a test creates a T2 server, it'll be the mock that is injected rather than the real thing. So we've got our mock of the server class, and then we're going to say for the new instances of this server class, we expect it to receive initialize run. So receive means we expect the test to call the server initialize run class. So this is something that the mock's already doing. It's checking that we're actually calling a method. So if we use this mock and we don't call initialize run, then a test will fail. Okay? So the mock's going to check that initialize run is called, and not only that, it's going to check it's called twice. So the test I'm running is going to create a new instance of the server, and it's going to call initialize run twice. And if it doesn't do that, the mock's going to complain, and you'll have a failed test. Then we say it's going to be called twice, and it's going to raise an error, and it's going to return a URL. So this means the first time we call initialize run, it's going to raise an error, and the second time it's called, it's going to return this URL. And this is really useful, because what I'm doing here is I'm checking something internally that's going to call. This initialize run is going to call an external service, but it's mocked, so it's not going to do that. It's just going to pretend it's going to do it. And the first time it calls it, it's going to pretend that the external service said, no, I'm at capacity. And then the next time it's going to do it, it's actually going to say, okay, we're okay now, and I've done this complicated thing, and I'm going to return you an address to the thing I've just made for you. And the reason this is so useful is that at no time ever does this initialize run actually call out to the external service. It's all faked, and it's just the mock is just pretending that it's at capacity, and then it's pretending that it's done some complex thing and returned what we'd expect it to return. And the reason this is useful is in my test for my code, which sets this up, I can check it that the first time I call initialize run and it fails, my code is robust to that and can reset, maybe wait a few seconds and try again, and then when I try again it works. So the reason this is useful is that, you know, if I was happy that my code would just fail if this fails, well, that's fine, I wouldn't need to do this. I could just have it, you know, receive initialize run once and only do the racing thing, and that's okay. But I don't want that to happen. I want my code to be robust to failures. So this allows me to say, first time we call it fails, but we're going to be robust. We're going to hang around. We're going to try again, and when we try again, we'll get the expected result. And so that means that there's doing a load of tests there. So there's ever so many things being tested there. So the first thing is the testing the code that I've written, which is calling this to check that it's not going to fall over when it gets an error, and it's going to be able to do the right thing when it gets a URL eventually. We're also checking that my code internally is creating a server and calling initialize run twice to get over this hump. And if any of those things don't happen, something will fail. A test will fail in my own code, or a test will fail within the mock that this hasn't happened. So that's an example of a mock, which is an incredibly useful tool within testing to decouple all of your code from any external things or any long-running processes that you might have to run. Because this could take like a minute to return this. So we don't want to be hanging around for a minute waiting for our unit test to pass. So let's just mock it out and return what we'd expect to get, because we're testing our code against what we expect to get. Now there'll be a load of other tests for the server itself, but we're not testing the server itself, we're testing something which is calling the server, and that's what the mock's useful for. Are there any questions about that? Good. Okay, right, so that's me done with testing and tools to help it. Now Caroline's going to talk about evidence.
So we're towards the end of the course now, and one of the things that's really important at master's level is to be able to critically evaluate and also to consider kind of a research approach to your work. So one of the things that we need to do at master's level is understand how to do research and understand how we can apply research techniques in our work generally. So this obviously is something you're going to be doing a lot of in the next semester and over the summer when you do your projects. Some of you anyway, certainly the ACS students. And it's something that is really important. And what we're going to do in this lecture now is kind of give you a bit of a heads up on some of the things that you might want to start thinking about, but also applying this to agile methodology and sort of its effectiveness. So it's like 2 for 1, okay? So we get understanding of research methods at the same time as understanding how effective agile processes are. So the first thing we need to consider when we're sort of thinking about how to evaluate something is gathering evidence. And we need to understand what evidence is, okay? So what constitutes evidence? So one of the first things that any academic will say if you kind of present some kind of argument to them is what is the evidence? And so you need to have some kind of data to back that up. So data can come in lots of different forms. We typically think of data as computer scientists, we typically think of it as being some kind of, it might be structured or numerical or whatever, but actually it comes in many different forms. So the first thing to say is that data, anecdotal data, which is things like conversations that you have with people, can be extremely useful. So it's not the most reliable form of evidence for lots of reasons, which we'll go into, but it is still useful, okay, and it does still constitute evidence. So when you are having a conversation with somebody about, oh, I tried this thing and I found this, actually, that's still a useful thing for us to understand. And of course, interestingly, people are far more likely to respond favourably to and rely on the things what their mates told them than they are really well-designed scientific studies. Right? We know this is how people work. So actually, when people make decisions in businesses, a lot of it is less to do with a really kind of detailed analysis and more to do with what they and their friends think. So this is not ideal, but it is worth bearing in mind that it's still a relevant form of evidence. Okay, so in terms of scientific evidence that we gather through research, there are a number of different ways that we can do this, and I'm going to take us through some of these in the studies we'll look at. So these are primarily observational, okay? So we have a technique called ethnography, where you would actually go into a company and observe what they're doing, or a situation, and observe what is going on and take notes, and this is a kind of technique that you might use. But a lot of the time when we're talking about evidence, so that's a sort of qualitative method, we're looking at things like case studies, where we're gathering information about what's happening within an organisation through things like interviews and surveys, through looking at their data, sort of speaking with people. So a case study is useful, but again, it suffers potentially from bias. It's more vulnerable to bias, I think is probably the right way of putting it. Then we have comparative studies. So it may be that we're collecting data out in the field, and we're comparing one situation with another. Okay, so this is slightly less vulnerable to bias, still in there. And then we have controlled studies, finally, and these are the kind of studies that you would use for testing whether, for example, a drug is effective or not. And the better controlled this is, the more confident you can be in the outcome of that study. So if you are trying to work out whether a drug is effective at preventing heart disease, then you want to look at this drug in a number of patients that are carefully chosen and count the number of them who have some kind of heart disease related complication over a period of time. So what often happens in those situations, and we're trying to the scientific community is trying to address this, is you find actually it doesn't have any effect on heart disease, but it does seem to do something about somebody's blood pressure, and therefore, we're going to mark it for blood pressure instead. This is not ideal scientific practice and has lots of problems associated with it. Ben Goldacre is an excellent person to look at in terms of evidence about that. So he's done some really good work on that. Okay, so let's go back to agile software engineering again. Right, so the first question we have to ask, if we're trying to evaluate agile processes, right, work out how effective they are, is determine what we mean by agile software engineering. Okay, we have a research question. We need to be able to determine what we're actually looking at. We need to really pin it down. So, what is agile software engineering? We've had flexible definitions, I think, over the course of this unit. So it could be following an agile method. So it could be following Scrum, following XP, following Kanban. Okay, this could be one way of defining it. It could be, so you notice that those are all multifactorial, right? So there are lots of variables. So distinguishing here between a scientific variable and the term variable that as we use it in computation. They're related but slightly different. So there are lots of variables in these, so lots of things that might change. So Scrum consists of lots of things. XP consists of lots of things, okay, which might affect results. So how do we know which is which? So we could instead look at certain processes. So we could look at things like pair programming, okay, so that pins it down a little bit more. We could look at TDD. We could also look at this from the perspective of applying agile principles. So this is pinning it down in a different way. So we're not looking at processes, but we're looking at things like, the philosophy of the team and the kinds of practices they follow there. So things like minimising waste, responding to change, involving the customer. These again are quite difficult to constrain. Okay, so we're narrowing down the definition in some ways, but what do we mean by involving the customer? Okay, how do we measure that? How do we define it? It's all difficult. So if we want to look at sort of what we should be examining, we can look at what researchers say is kind of the view that companies have on this. So in industry, there's a recent survey here that says the majority of firms use agile practices, and Scrum is the most widely used. They say refactoring is better than reworking. Interesting. So what this is about, I think, is applying the sort of agile approach to refactoring, which is more constrained than simply rewriting your software. Okay, so refactoring in the kinds of ways that Rob has been talking about earlier in the course unit, rather than simply rewriting stuff. This also claims that agile methods improve the quality of software, and it improves the ability to meet deadlines, and it provides a competitive advantage. So this is great. This is an industry-based article. I am not sure about the vested interest of the people who have commissioned the article, but it's all very positive about agile. So that's lovely to see. But we maybe want to look in a little bit more detail at some individual studies to see where people have actually. So this is based on a survey where people have actually kind of looked at those practices in detail. So we can see that companies are employing agile methods on a kind of a greater basis over time. So we know that more people are likely to employ agile methods now than they were, say, 10 years ago, 15 years ago, and this is growing over time. The kinds of practices that people use might be things like code review, continuous integration, unit testing, iterative development in Scrum. And in terms of applying the practices, we often find that challenge is at the management level. Okay, so it's generally the case that evaluation is easier when we're looking at individual practices than it is when we're looking at large kind of larger applications or applications in the large in terms of agile methods. So this is a systematic review that was done a while ago. So a systematic review is where you look at all of the research that's been done in a particular area, and you ask very specific questions of it. And so instead of looking at one single study, you're able to gather together the evidence from many studies and use that to answer the question slightly better than you might do with an individual study which might be biased. So, if you look at the overall literature, things like management support, attitude, motivation, team composition, training and technical expertise all seem to be important, okay? So these are things that we've touched on previously. I think that, again, it's interesting here, because we can see some of these things as being quite sort of high level, okay? And these are things that people have reported in the literature as being important. But again, it's quite tricky to understand what we mean by them. So a more specific study is one which looked at adoption of Kanban at the BBC. Okay, so this is quite an interesting one. So they went from using their existing system to introducing a Kanban system. So this was a basically issue tracking ticketing system, essentially, where they were using a Kanban board to manage their work. And they found this was a production system, so it's being used, and they found that the number of live defects fell by 24%, okay, which is good, so that's great. They also found that productivity improved, so lead time fell by 37%, so lead time is basically the amount of time it takes for a particular issue to be addressed. And the release frequency increased by a factor of 8. So they were able to go from releasing relatively frequently, every couple of months, to releasing much more frequently than that. So I think people have talked about this with regard to continuous deployment. So the interesting thing about this, though, is that 50% of the teams in this study were using Scrum beforehand, okay? So actually, they weren't using Waterfall, they were using an Agile method, and by changing that method, that's what led to these improvements. So why wasn't Scrum, this is the interesting question for me, why wasn't Scrum working in those environments? And I think the researchers felt that there were a couple of reasons for this. It was partly that they were working on a legacy code base, and this simply was not set up for using Scrum. It just didn't support. It was very convoluted and complex. There was an awful lot of technical debt associated with it, and it was very difficult to kind of implement new functionality in the way that Scrum demanded. There was also a lack of feedback as well. So the way they were working, they were getting very, very little feedback from the customer, and they felt that this was not something that was really conducive to using Scrum either.
Excuse me?
Yeah.
Do you mean why Scrum wasn't working in this case or in general?
So this was in this particular case, yeah. So this is one specific study. So it may be that the reasons that we see in this study, which are things like working with a legacy code base, lack of feedback, they might apply to other projects, but we don't know because it's only one study. So we don't know whether we can generalise these results.
Okay. And what do you mean by live defect?
So this is in the system that people are using. These are bugs in that. So a live defect, yeah, it's where the system's actually, people are using it and it goes wrong. Yeah, absolutely. Okay, so Agile methods can increase productivity. So we've got a study here looking at two similar projects, one using XP, one using traditional development methods, and we find a 42% increase in productivity for the Agile team. Interestingly, the difference was largest in the first iteration. Okay, so it's possible there's something going on here called the Hawthorne effect. So I don't know whether people have heard of this. Basically, this is where you change something and people respond accordingly, and they're very highly motivated, and the change itself is enough to improve something, and after that it falls back to a baseline again. In another study, an old release with traditional methods was compared to a new release developed with Agile methods, and there was a 46% increase in productivity. But we've got a confounding factor here. So a confounding factor is basically an issue where something co-varies with the variable under question, the outcome variable that you're interested in. And in this case, it was that the Agile team had greater domain expertise and programming expertise. And then if we look at similar software, so not the same software projects, but two similar ones, slightly different and different approaches, we find that XP was 337%, wow, that's a lot, more productive than VModel. So VModel is essentially a type of waterfall. But we have to look at what they were measuring. So they weren't looking at functionality per se, but rather at features. There is, to counter this, some evidence that productivity decreases with Agile methods. So we've got one study saying that an XP team was 44% less productive than comparable traditional team, or there was no change in productivity following the introduction of Agile processes. Although, again, Hawthorne effect, potentially productivity did increase in the first iterations. So we see here sort of two sides of it. So there's some evidence of a productivity increase, some evidence of productivity decrease. Okay, so we have to kind of think about, this is why it's important to look at more than one study. We have to sort of think about what the overall results are telling us.
This is the only negative one. Which one is the negative besides the BBC?
Oh, so this, well, I'd say this was negative. So this is where they compared Agile. So here we had a team doing XP, which was compared with a traditional team, so essentially a waterfall team, and they found that the XP team was less productive.
This is the only one against the Scrum.
So this was against XP. So this
Extreme programming.
Yeah. So they were looking at XP in this particular situation. So is it the only study that shows that Agile methods are not effective? Nope. There are hundreds, if not thousands, of studies looking at Agile methods, and some of them show that they are better and some of them show that they aren't. So there's, on balance, most of the evidence is in favour of Agile, but I guess what I'm saying here is that not all of it is. Yeah, and understanding that, because it's a very complicated situation, okay, making a decision about how to apply a software method in a sort of industry environment or production environment is very challenging one, right? So there are loads and loads of things, different things you need to consider.
And this is right. We can't agree 100%
Absolutely.
on one thing.
Indeed. So this evidence can kind of help us with making those decisions, but these situations are always going to be complex, and so there's never going to be one single study that's going to give you everything you need. Yeah. Yeah.
What does XP refer to?
Oh, extreme programming. So extreme programming is another Agile method that is similar but slightly different to Scrum. Okay, so productivity as measured by, for example, lines of code or functionality, or however you want to define it, is one thing. But what about quality? So quality is really important. So there is some evidence that Agile processes help to increase quality. So we've got a single software project here. We have a new release and an old release. And what we found is that in terms of pre-release quality, so this is internal quality of the software, the internal structure of the software, 65% improvement. And then in terms of post-release quality, so I guess this is external facing, so how many bugs were found after it was deployed, we're looking at a 35% improvement. So this is pretty good, actually. This is definitely worth having. So we've got an XP project here compared with a non-XP project. Customer reported 13% fewer defects. Again, not bad. And we've got another study showing that an XP team's code is consistently higher quality. But to counter that, there was higher productivity in the traditional team, and interestingly, a better user interface as well. So there we go, different teams.
So the higher the gap that we have between the pre-release quality and the post-release quality, the better the Scrum is practices was deployed.
So So what we'd like to, yeah, that's right. So what we'd like to see with both of these, so we would evaluate these separately, and we'd like to see an improvement in both, yeah. So the improvements in pre-release quality is important because anything that, so if pre-release quality goes up rather, then post-release quality will go up as well. Because
it should go down. The first one should go up, the second one should go down.
So if there is an improvement in this one, you should see a decrease in bugs in post-release, yeah, which would be the same as an improvement in quality. Depends how you define it, but yes, fewer bugs, right? So we want both of the, so improvements in quality in both cases means fewer bugs, basically. Right, so the final study, looking at 10 traditional teams and 10 XP teams, didn't find any difference. You know, it's thereabouts. So there was a survey that was done recently. So those were kind of looking at metrics associated with the software, so quality, productivity, lines of code, number of defects, this kind of thing. So this is a slightly different kind of study, and this was looking at agile adoption. So this was looking at a particular company who introduced agile methods, and it's by and large a very positive paper. So it was talking about the extent to which the software had improved, and also the team working environment had improved. And I think there are a few really interesting things that I want to just pull out of this. So I say here it's a perceived improvement across the board. So what we found in this situation was that the software engineers, the developers, and the management teams felt that this was a good idea, right? They felt that introducing agile processes resulted in improvement across the board. They didn't really measure it though, okay? So this was more at the level of how people felt about it than kind of evidence through metrics. That's very important. And so the reason it's important is because how people feel about things is going to influence how they act, right? So as I said before, the evidence, the kind of cold hard figures, which we should respond to, we're very bad at, whereas if we feel that something is a good idea, then we're much more likely to do it. So feeling is much more important than thinking in these situations often. Okay, so what specifically was causing this though? So the first thing was improved teamwork. So we had improved motivation, a better common understanding of what was going on, better common understanding of the code base, and also the team was better at learning. So teams were better at working together and learning. So this is an interesting one. So they termed it work pride, okay, this particular variable. And the really interesting thing about this is that all of these things improved, so they went up in terms of how people felt they were compared with the year before, and they felt that their team was making more of a contribution. But my favourite one, and this is the one that was highest, was that they themselves felt their contribution had improved more than the team actually. So individuals felt that they were contributing more. They felt that the increase in what they were contributing was greater than the increase in what the team was contributing, which I think is interesting. So I don't know how those map against each other, but this is obviously a very positive thing. So individuals were quite happy about this as well. So of course one thing to note with this kind of study is that this was post hoc data collection. So you're asking people about things after the fact, okay? So they didn't have a sort of a pre-training reference point, okay? So they learned how to do this agile stuff, and then people asked them afterwards, oh, was that a good thing that you did? And they said yes. But actually, whether it was or not, we're not sure. But people seemed happy enough, so this is important. Okay, so let's look at another practice. So we'll pin this down a little bit more. So we're going to look at some controlled studies now. Pretty much, yeah. So post-controlled studies in software engineering, it may not surprise you to learn, are done on students. Okay, so this is a situation in industry. People tend not to take risks with this stuff, but yeah, our students, right? Well, yeah, it's fine. We can run studies on them as they're learning. Okay, so this is a student project that involved pair programming. So, what we found in this particular study was that when students were in pairs, development took 15% longer. So what this means is that if you take the cumulative total of what people would be spending on it, doesn't mean that a function that took someone to implement took, one person to implement took 2 hours if 2 people working on it, and 1 hour if one person was working on it, but rather that it was 15% longer. So, yeah, an hour and 10 minutes or something. So, the software had 15% fewer defects though, so we've kind of hypothesised, haven't we, that pair programming is helpful for reducing defects, very important, so, and this seems to have the effect. And students enjoyed it more, yay! Is this what everyone here has found? You enjoy programming more when you're doing it in a pair? Yeah. I can see some people nodding and other people going. Right, okay, fine, good. Here's an important one. Improved design, and the way they measured this was that you could have the same functionality in fewer lines of code. So it is not always the case, by the way, that the sort of an optimised solution is the most readable. You get to a point where that is absolutely not the case at all, things like HPC. But here, they were looking at it as being basically tighter code. And they also found it improved learning. So one of the benefits of this from the lecturer's perspective was that there were fewer queries. So this basically means students are working together and they're working out the problems themselves rather than working individually and having to ask somebody about it. And actually there's loads of evidence that if you're able to work out the solution yourself, thus making the job of the lecturer redundant, you learn much better. Okay, so we haven't quite perfected this yet, but this is the utopia we're aiming for. Okay, so let's look at another study, another pair programming study. So this time, looking at 46 students, development took a bit longer this time, so it's almost 50% longer for pairs. But again, functional correctness was vastly improved. So individual programmers got 6.5% of functions completely correct and 6.5% of functions incorrect. And that means it failed all of the test cases. Whereas pair programmers got 18% completely correct, so almost 3 times as many, and no functions completely incorrect. So we have no functions failing all test cases. So again, this is really nice evidence in a controlled environment that pair programming really helps to kind of pull up quality. And just before we break, I'll just introduce you to test-first programming. So test-first is slightly different to test-driven development. So with test-driven development, if we're following it very rigidly, we write one test and then we write the code to pass that test. With test first, it's really about writing tests first. So it might be one test or it might be more than one test. And some of you might be thinking, oh, that is more what we've been doing actually than test-driven development. So anyway, so this is fine. It's another way of looking at it.
What's the difference?
So the difference is, if we're looking at test-driven development, we're doing it, being very dogmatic about it. You would only ever write one test. Okay, so the sort of red-green refactor cycle is followed very, very tightly. Whereas in test-first programming, people might sit down and say, okay, so we've got a number of criteria here, and what we're going to do is start writing the tests that will help us understand whether we... yeah. So you might write all of them, you might write some of them, but the point is you're writing more than one. So you're thinking about how you want to test your software before you write the production code, but you're not being kind of dogmatic about the number of tests you write. Okay, so test-first programming. So 39 students this time. Development took 12% longer than if they're just writing tests after. It resulted in 40% greater coverage, which I think is pretty good. There was no difference in terms of functional correctness, so no difference in terms of the actual code. But we did find here that some test last participants, so those who were encouraged to write tests after they'd finished writing their development code, did not write any test cases. So this will definitely be familiar to people, presumably because they didn't have time or they didn't think it was necessary. So it may not have mattered in this situation, and indeed it didn't, because the functional correctness didn't seem to change. But when we're looking at writing much bigger systems, then having greater test coverage is probably sensible. Okay, so what I'll do is I will finish there, and we'll have a break for 10 minutes. So we'll come back, let's say come back at 12. Okay, so test-driven development, another favourite practice, I know, of people in the room. So this is quite a nice book chapter, actually. So this is a paper that's written up as a book chapter. So this is available on Blackboard. 32 trials were looked at here. So this is a review of 32 studies. So they took a systematic review approach, so they collected together this data, and then they essentially, I don't think they used this term, but they performed what we might call a meta-analysis on it, okay? So they applied their own criteria to the results to kind of draw wider conclusions that we might have a better chance of generalising from than we would do in an individual study. So I've got some tables coming up. Contain your excitement. Oh gosh, they're not very good tables either, are they? That's not excellent. Okay, right. So assume that says controlled experiment there. Right, so what we've got in this table is, of these 32 studies, is the type of study. So we had controlled experiment, pilot study, industrial use, so this is observing things actually used in the wild, and this is just the total running along the bottom. And what we find, what we've got here is whether TDD made things better, worse, mixed, sometimes better, sometimes worse, no real difference, and then we've got the totals running down here as well. Okay, so we also have these numbers in brackets. So this is, the number here is all trials, and these are where trials where good TD practices are known to be applied. So this is to do with the rigour of the research. So again, it's to do with how well things were defined. So where people within the studies had defined precisely how TDD was being used, these are regarded as basically better evidence than where people just said, oh yeah, we did TDD, but actually we don't know the reality of that, we don't know what that really meant. So, so internal quality. So this is looking at the structure of the software itself, so the internals of it. And what we found was that if we just look at the totals along the bottom, so it seemed to be better in around 5 cases, worse in 2, mixed in 3, sometimes better, sometimes worse, and no real difference in 4. So this provides us with, so it's interesting, so this provides us with some evidence, I would say, that it was better. I've got 5 there. It's good seeing 5 against the 2 where it actually got worse. So internal quality getting worse, which I have to check those studies, actually. I don't know whether I've read the details of those. And then we can see sort of mixed or no difference. So, you know, this is kind of tentative, maybe, evidence. What about external quality? So the difference here, it seems to be much bigger. So external quality, which is basically where you're looking at the user-facing part of the software. So when the software is out there and being used, are defects occurring there? TDD helped or improved things in 13 of the studies, whereas it was worse, which is not ideal, but it's only in 3 of the studies. And then we found that there was no difference in 6 of them. So external quality, I would say, on balance, TDD seems to be making a difference here. What about productivity? So again, productivity is not defined here. So it could be lines of code, it could be features, or something else. And what we find here is that teams were more productive in 10 cases, less productive in 9 cases, and then there was no difference in 6. So what can we say here? 10 against 9. What can we conclude from that? I would say Not very much. Okay. So what they haven't done here. So I talked about this kind of meta-analysis technique. What they haven't done here is applied any inferential testing. So this is all descriptive. So you have statistics that are descriptive that tell us about what's going on, and then you have statistics that are inferential, which allow us to draw conclusions about differences. So they don't use inferential testing in this case. Probably it's not really appropriate to, because the measures are all quite different, the studies are all quite different. But if we were to look at this difference, and we had a much larger sample, we could perform some inferential testing to decide whether this is what we call statistically significant. So essentially how likely it was that it occurred at random. And we haven't done that here, but I would say that given the numbers involved, we cannot be confident that a difference of 1 really is something that we can rely on. Okay, so I'm kind of saying that might be that difference is real and did not occur at random, but we can't be confident. Okay, so test quality. So this is the quality of the actual test, which obviously is another important thing and has knock-on effects elsewhere. And we find here that it's better in 10 cases, worse in 2, and there was no difference in 5. So
what does mixed mean?
Mixed means that within those particular studies, in under some circumstances it was better, and in some cases it was worse.
And what is the difference between mixed and no difference?
That was where there was a study where they basically didn't find a difference between the two. Okay, so it was the same. So mixed is slightly, it's subtly different. So if something's mixed, you could conclude there was no difference. But what it meant was that the results of the study found under these circumstances it was better, under these it was worse, or in fact in one team there was an improvement and in another team there wasn't, that kind of thing. So again, it means it's inconclusive.
I find striking, it's 0 for this one and the one before.
Yeah, that's possibly to do with the study design though. So it may be that in those studies either they just didn't detect a difference at all, so we see here that there's no difference, or it could be that, so it may just be that category just doesn't apply.
I mean, since it's 0 on this slide and this slide before,
Yeah.
do we need the mixed at all?
Yeah, that's right, yeah. So none of the studies reported mixed results.
So does the 0 give an information or no?
Well, it tells us here that so it depends how we want to categorise the information. So what it's doing is telling us here that none of the results within any of the trials were mixed on this particular metric, for want of a better word. It's not really a metric, it's a kind of category, I guess, that we're judging on here. So it was in this one, internal quality, but in the others it wasn't. Does that make sense? Yeah. Okay. Right. Tool usage. Okay. So here's a really nice one. So we've looked at kind of just thinking, do agile practices make things better or worse? So this is one looking at tool usage rather than practices. And this one found that product backlogs and burn down charts cause catastrophic failure. I think is a lovely result. Okay, so why on earth would this have happened? Okay, so some of you may be able to reflect actually on your own experience within the project as to why this might have caused the problem. So in this particular study, what they found was, and this was done in industry as well, which is why I particularly love it, like this actually happened. So what they found was that the emphasis on measured productivity obscured communication about software quality. So you know, if you give someone a metric to work to, it will always change their behaviour, right? So this is one of the major problems with metrics. So basically, people were so focused on making it look as if they're doing loads of work, is my guess, that they failed to actually do high quality work, let's say. So this really is about a management failure rather than a tool failure. So we need to be careful when we evaluate this kind of evidence. What we don't say is, oh, we must never use product backlogs or burn down charts because they're going to cause catastrophic failure within our company, because they probably won't. But what you need to make sure you do is don't use those in place of like actually writing good software. Okay. So a final study that I'm just going to mention is this one by Richter et al., which talked about problems with agile approaches. Okay, so this was an interview study again, where they asked a number of people what they felt were some of the issues with applying agile approaches. So we've talked about limitations of them in terms of, oh, you need management to be supportive and and so this is all fine, but this was focused a little bit more on the principles themselves and what the problems were that people perceived to be with the actual practices themselves. And I think it's quite interesting. So we talked about how about developing with agility and things being very flexible and this kind of thing, which is fine, and I'm quite happy with that, right? I'm very relaxed about these things. I'm kind of, I'm quite happy to embrace change and work with agility, but not everyone is. And one of the issues that was identified within organisations was the rules of agile approaches are very blurred, okay, and this is not always a good thing. And one of the reasons it's not a good thing is because it causes problems with scaling. So within one team, you can have your fantastically self-organised team, right? And you all get on really well, and everything goes swimmingly, and this is all fabulous, and you're doing loads of work, great. But then you try to scale that, and you find that not everyone or not every team will behave exactly like your team. Okay, there are going to be differences there, and actually the rules that apply in your team may not apply in another team, and so actually how we take within an organisational setting, how we scale that is a challenge. So it's underspecified, and people don't always like underspecification. Okay, they like things to be a little bit better defined. There's also found to be a misunderstanding of the application of these things. So people would apply these what they perceive to be rules in different ways, and not everyone had the same understanding, and then this caused some tensions there. Lack of organisational support was also mentioned as well, and in particular the things I want to draw attention to here are misunderstanding on the part of the customer, so the customer just not really understanding how agile methods work and therefore not engaging properly, and that was definitely a problem. And also, this is interesting, they were imposed on the team, and teams. So paradoxically, a team is saying that it doesn't like to be self-organised, which in itself is self-organising to some extent. But anyway, teams didn't like having these principles imposed on them. Okay, so they were saying actually I'd prefer to work in a different way. Yeah.
Do we know if attributes like the average age of the team and stuff like that affect if agile?
Ooh, good question. So I don't know personally of any studies that have looked specifically at age, but it is the case that newer companies tend to be more likely to adopt agile principles.
I would expect the same.
Yeah. Yes, I agree.
Yeah,
I would
that's
hypothesise that would be true as well. But so there may have been some work on it, but I'm not aware of any specifically. But it's something that it's an interesting question. Yeah, and so
or even the technology they use, for example, the programming languages.
Yes, I think so. Yes, there is an association with programming languages and technologies and infrastructure generally. So that makes a difference. So I mean, because one of the things, it's not quite what you're suggesting actually, but one of the issues is that if you don't have the right infrastructure.
No, for example, if there are people that they have used to work with more traditional, for example, programming languages, that might be a hint that they don't like to change the way that they work.
Yeah, interesting. I think that's quite a complicated socio-technical question.
Yes.
Yeah. Okay. but an interesting one. Yeah. Okay, right, so just before we finish on this, I want to just leave you with this, because this is something that you should think about, not just in regard to this course unit, but in regard to all your course units and your projects and life in general, which is how reliable is the evidence, okay? So we need to think about these things when we're evaluating evidence. Reporting bias. Are people telling you the truth? Are they telling you something because they think it's what you want to hear? So as a researcher, an investigator on a project, and I go and interview someone, and I'll say, oh, do you really like using agile methods? And they'll say, oh yeah, I really like using them, because they're like, oh, well, this person's obviously enthusiastic about them and they want to. So this is definitely a problem. Selection bias. Am I only going and talking to people who I think are going to give me the answers that I want? Are the people who volunteer to take part the people who are really interested in the study, and therefore we're not going to get that dissenting view that might come from people who are less interested in the study. Lack of a consistent metric, massive problem in software engineering. Okay, in something like physics, they are a bit further down the road, and they are much better in terms of understanding how they should measure things and what units they should use for measuring and this kind of thing. We do not have that in software engineering. We have enormous literatures dedicated to people arguing about how you should define productivity, for example. Often with these kinds of studies, we have a lack of a baseline. Okay, so when you're doing anything in the real world, it's really, really hard to pin down the baseline. So if you're evaluating your new machine learning algorithm, then you will usually have a really consistent baseline. Okay, so you can use benchmarking data for evaluating your algorithm. I would say in that situation that the thing you need to be careful about there is external validity. So you might have like internal validity because you've got the benchmark, which you know you can evaluate against. You know what previous results for other algorithms are, but actually would that apply with different data in the real world? Often not. So I'm not going to get into a rant about that now. Okay, so confounding factors. Are things co-varying? Okay, is it possible to be able to measure what's happening to the outcome variable without something else changing at the same time? So you're trying to understand whether it's X or Y, but X and Y seem to be co-varying. You know, how do we manage that situation? It's very difficult. And finally, I just mentioned briefly external validity. So whatever happens in your study, whatever results you come out with, is it the case that those are really the results you're looking for, or is it the case that this would really apply to other situations, or is it the case that actually they only apply to the specific situation you're studying? And this is very, very common in science. So this is really, really common to not be able to replicate results. Okay, this is a big issue. Right, so I have helpfully put online all the research papers that I discussed today, and I think also we have an example of how tooling can help support safety critical engineering as well. So that's all on Blackboard. There's loads of other, if you feel yourself fired up about looking at the limitations and evaluation of agile processes, there is in the ACM Digital Library many other papers that you could read should you wish. So I'll finish talking about our evaluation there. Does anyone have any questions about that?